So this is example 7, working problems number 7. So these questions is a bit lengthy, okay? So because it requires you to prove out certain formulas. So a disk of radius r is rotating freely in its own horizontal plane about a fixed vertical axis with an angular velocity of omega. And a second similar disk is placed on its upper surface. The second disk is at rest initially, and its center lies on the axis of rotation of the first disk. Now the surfaces in contact are rough. What common angular velocity will the disk eventually rotate? They want you to prove out the formula, okay, to which what is the common speed that when both the disks are in contact. Okay, and then the last part of the question, they ask us to prove the energy loss in the process as a fraction of initial kinetic energy. Okay, if the load of the upper disk is evenly distributed, means you can consider this as uniform pressure, because they say the load that is distributed is uniformly distributed over the lower one. Show the time during which slipping occurs is given by 3 omega r over 8 mu g. Omega is the common speed, r is the mean radius, coefficient of friction, and this is gravity. Because we know that they say already the weight of the upper disk when it lies on the lower disk, the load is equally distributed, evenly distributed. Okay, the load. That means the weight of the upper disk. Okay, mu is the coefficient of friction between the surfaces in contact. So now we start off the question by drawing diagrams. I have drawn the diagrams here. So this will be the lower disk, pink color, and then this will be the upper disk, okay, blue color. So initially is at rest. The second disk is initially at rest, and then finally it will bring it up to into contact. So they are lying in horizontal plane, and they are rotating in the same axis. Okay. So the load of the upper disk will eventually be equally distributed on the lower disk, okay, the surface, the upper surface of the lower disk. So you have to consider the mg, the weight of the upper disk, will be acting on the lower disk, and which is equally distributed. Okay, so this is before impact, this is after impact. That means before contact and after contact. So before contact, you must consider each of these as individual rotating component. Then after contact, then you have to consider both of these as one. And this should be the mean radius. This should be the mean radius of the whole thing. The radius of the disk. Okay? So part A, the question asks us to find the angular momentum. Sorry, the question asks us to find what? First part, common angular velocity. They want us to find the common angular velocity. So what we can do here, we can apply the principle of conservation of momentum again, before and after. So this is before and this is after. Okay, before contact and after contact. So omega 2, they say initially the initial speed of the second disk, the initial speed, is 0 because the disk, the blue disk, is at rest initially. So therefore, from the upper equation, it reduced to something like this. This is what we want, the common speed. The common speed. Since I1, I2, and I are the same, identical, because the question say identical disks. Okay, they are identical. In the question, they have mentioned identical disks. So therefore, you take I1, I2, and I are the same. So you can change all these to I, the moment of inertia. So you have this equation. Once you manipulate, this becomes 2I. So when you bring a 2I over to the left-hand side, so it will be on the denominator side of the equation. So the 2I. So strike off I. So you have the common speed should be equals to omega over 2. The common speed should be the speed divided by 2. That means half the speed once they come into contact. Okay, so the first part is proved. Okay, the first part is proof. So they say the second similar disk. So that is why the I are all the same. Okay, so and then they say the second disk is initially at rest and it lies, okay, its center lies on the same axis of rotation. The surfaces in contact is rough. With what common angular velocity will the disk eventually rotate? So the answer is half omega. Okay, the first part. Now the second part, the kinetic energy of the system before and after contact. So we have to find the kinetic energy before they come into contact and after they come into contact. Okay, so we have to know, okay, the kinetic energy loss actually. Okay, the question asks us to find the kinetic energy loss. So the angular kinetic energy before contact. So we have this, each individual. But then omega 2, that means the initial speed of the second disk is at rest. So the omega is 0. So this part here will be 0. Okay. So the angular kinetic energy after contact. So you have this combined. Okay. So and then we know that omega common is equals to half omega. So you just substitute half omega here. And then the I are all identical. So you have 2I. I1 plus I2 become 2I. Okay? So you have the kinetic energy. The final kinetic energy is equals to 1 over 4 of I omega squared. So the kinetic energy loss that you have, okay? And then that is 1 over 4 I omega squared. That is the amount of kinetic energy loss. Then this as a percentage of initial kinetic energy. Okay, so you have this percentage kinetic energy loss. So you have the initial, okay, and then the percentage of initial kinetic energy, the initial, and this is the final. So it's 50%. This is the initial, this is the final, 0.25, and this is 0.5, okay? So you got 50%. Kinetic energy loss is 50% from this. Then the next part, the width of the second disk here, they ask us to prove out the formula. So this is a bit, okay, messy, okay? Quite a lot of things you have to prove, okay? Complicated. Now the width of the second disk is evenly distributed on top of the first disk. Therefore, the pressure distribution on the surface of the first disk is considered as uniform. So I have this diagram here. So this is after contact. So the width of the upper disk, that means the blue disk, is evenly distributed on the lower disk. Okay, we know that width is equal to mg. So we know that pressure equals force over area. So the area of this surface area of the purple disk is pi r squared. So the weight, that means the force of the load, the weight of the blue disk which is on top is W, the force. So, and in normal friction clutch, what we have is the actual spring force or the normal force. So the normal force that is acting here on the surface of the lower disk is W, which is equals to mg. Now consider an elementary ring. So what we do is consider this an elementary ring, the thickness of dx with the radius of x. So we have the area of the elementary ring. The area of the elementary ring to be 2 pi x, that means 2 pi r, the circumferential length, then multiplied by the thickness of the ring. This is the thickness of the ring, delta x. So, and then we have the force acting on the ring is not the whole thing, and it is only the force that is acting on the ring and not on the entire surface. So that is why it is placed as delta W, considered as delta W. Okay, so that is the pressure multiplied by the area. Pressure times area. You get the force. So the frictional or tangential force, that is the surface in between the two disks. Now, this is the frictional force. Between the two, you will have friction created because both surface is rough. So you have mu Rn, okay, mu Rn, that is for the ring. Yeah? I put a subscript x here, that means it's for the ring. This is not the radius, this is for the ring. And it is equals to mu delta W. Delta W, okay, is the normal force actually acting on the lower disc. The normal force that is acting on the lower disc. And since frictional force or the tangential force is equals to mu times normal force, and which normal force is equals to this, so you have the friction is equals to the product of this. So by substituting the delta W, which is the whole thing here, over here, so you'll be able to find out your frictional force, and then torque is defined as tangential force times radius. The tangential force that we have here is the frictional force. Okay? By substituting your x into the whole thing, so you got your torque formula. Then after that, what you need to do is you have to find out total torque. If you want to find out the total torque, you can integrate the whole equation with respect to this side with respect to x, and this side here with respect to the t. So you get a total t. Okay, so total torque transmitted. So you integrate. The limit is from this center point here, which radius here is 0. So you just pull this back to the center is 0. So the limit of the surface is from 0 to the entire surface, that is r. So that is why your upper limit is r and the lower limit of the integral is 0. So x squared delta x, we know that integration of x squared, you get x cubed over 3. Yeah? So you have this r cubed over 3 when you put in the limits of r and 0. Okay, so you have the torque formula. Now what is required is the time. Okay, so that is the torque. So for the time, based on Newton's second law, you have this. And we know that alpha is equals to omega over t, right? So we can just put in, and I is equals to mk squared. Okay, so the I equals to mk squared. The k is r squared over 2 for a solid disk, which you have studied in dynamics, yeah? And your k, which is the radius of gyration for a solid disk, is equals to r squared over 2. So that is the moment of inertia. This is the angular acceleration. So everything put it together, so you'll be able to find out your alpha. And since alpha is this and omega is this, we can find out the time here, changing the time here as the. So putting everything alpha, you'll come to this final formula which you have proved. This is what they wanted us to prove. This question is a little bit tedious, but then it gives you at least it gives you the idea how a discharge operates. Okay, and then when they consider it as a disk, you will be able to, okay, you must be able to prove that the time period is equals to this what is given here. Thank you, everybody. Stay safe. Stay safe.